In this section of Chapter 8, I would like to go over Lewis structure and formal charge. Make sure you have a periodic table in front of you while you are learning these topics. Lewis structures are representations of molecules showing bonding and non-bonding electrons. In these two examples, in case of H2, this is a bonding pair of electrons. In Lewis structure, electron pairs are shown either with two dots or by line. Similarly, in case of Cl2, this shows a pair of bonding electrons, and non-bonding electrons are shown with two dots around the Cl. In many cases, we'd use lines rather than dots so that they're more visible. So keep in mind, each line would represent a pair of electrons. Now here we're going to discuss how to write down Lewis structures. Our first example would be PCl3. Now make sure you have a periodic table in front of you. First, we need to get the valence electrons. And you need to have the sum of valence electrons for all the atoms in the molecule. So in case of PCl3, first we'd get the valence electrons for phosphorus. If you look at the periodic table, let me put a dot, red dot on phosphorus so that you know the location of phosphorus. Okay, this is phosphorus. You can see here phosphorus 15. Now that's atomic number 15, but that's not what we need. We need outermost electrons. So you count from the beginning of the line where phosphorus is in. That's line 3. So you count from left to the right. If there are transition elements, you skip transition elements. So now here it'd be 1, 2, 3, 4, 5. So there are 5 valence electrons on phosphorus. In other words, it's 3s2, 3p3. So s2p3, that gives 5. Now let's look at Cl. Cl is, if you look on the right side of phosphorus, next to phosphorus is sulfur, and next to that is Cl. Again, I'm trying to pay your attention. Okay, so that's Cl. Now you count from left to the right until you get to Cl. Only s and p electrons, and obviously there is no transition element in between, so it's straightforward. You can count from the beginning of the line until you get Cl. So it'd be 1, 2, 3, 4, 5, 6, 7. So there are 7 electrons per Cl, and there are 3 such Cl in PCl3. So that's why 3 times 7, 21, and then you add 5. So altogether we must have 26 electrons. So keep that in mind. This is the first thing you need to do. You need to sum up all the valence electrons or outermost s and p electrons in polyatomic ions or molecule that is given. Now if you have a negatively charged species, then add extra electron. If it's -1, that means add 1 extra electron. -2 means add 2 extra electrons. If it's positive, take away electron. If it's +2, take away 2 electrons from the total. So keep these in mind in order to get the total number of valence electrons. Now we already calculated the valence electrons for PCl3, so let's write down that PCl3. The total number of valence electrons is 26. And when you write down Lewis structure, we must account for all these 26 electrons around this compound. Now, PCl3, now we need to pick the central atom. Usually central atom is the one which is least electronegative other than hydrogen. Of course, if you have hydrogen, you cannot place hydrogen in the middle because hydrogen cannot have more than one bond or one pair of electrons. Because when hydrogen gets one pair of electron, it gets configuration of helium, the closest noble gas. So keep this in mind. Most other cases also you'd find that central atom is present in least number. So in this case, phosphorus is the least electronegative, and also phosphorus is present in least number, which is 1. So let's put phosphorus in the middle, and 3Cl attached to phosphorus. So that's what you need to do. Put the central atom, outer atoms, and join outer atom to the central atom by at least a pair of electron or a single bond. Pair of electron is same as a single bond. So that's the next step. Now we'll move to the next slide. Now you need to fill the outer atoms with noble gas configuration. So let's write down Cl, Cl, Cl. Remember, we had 26 valence electrons. We are going to account for that. Now, we are going to work on outer atoms. Right now, we don't pay attention to the total sum. We're going to think about it later on. So let's work on each Cl with pairs of electrons. Pair, 2, 3 pairs, that makes it 8 around that Cl. 2, 4, 6, that makes 8. 2, 4, 6 makes 8. Now I can count. 3Cl would have altogether 24 electrons because you count all around Cl. Let me show you one such counting. So that's altogether 8 because 3 pairs are non-bonding on Cl and 1 pair is bonding between phosphorus and Cl. But you're going to count all of them. So right now we have 24 electrons, but we're supposed to have 26. Question is, can you put that extra pair on Cl? Answer is no, because Cl has already 8 electrons. So in this case, you need to put extra pair of electron on phosphorus, which would also at the same time get noble gas configuration or 8 electrons around. So that's it. That's going to give Lewis structure for PCl3. Sometimes you have quite a few extra electrons. In that case, you break the noble gas configuration or octet rule for the central atom, but not the outer atom. So outer atoms are rarely show exceptions. It's mostly the central atom. Now here we're showing you more examples. HCN. Again, you first count the valence electrons. Let me show you that. Hydrogen is 1. Carbon is 4. Again, make sure you have periodic table in front of you. Either you go by electron configuration or just count from left to the right until you get carbon. So carbon has 2s2, 2p2. S and p electrons added together, outermost obviously, with 4. Nitrogen would have 5, 2s2, 2p3, or just counting from left to the right. So altogether we must have 10 electrons. Now, central atom, you cannot place hydrogen in the middle, so you put carbon, least electronegative. So HCN, and then join them by at least single bond. And now work with outer atoms. So we worked with this nitrogen, 6 pairs of 6 electrons we added. So altogether now we have 8. Now we have altogether 10 electrons. But there is a problem you see with the carbon. Carbon has only 4 electrons around, but you'll have to make it 8. So that's why we're showing you here at the bottom, a pair of 2 pairs of electrons are moved in between carbon and nitrogen. Each pair makes 1 bond, so 2 pairs when you moved, so there'll be triple bond between carbon and nitrogen. Here we're going to discuss formal charges. Formal charges allow us to identify the best Lewis structure when there is a possibility of more than one Lewis structure. And I'm going to explain to you how to come up with these formal charges by going over the example of carbon dioxide. So carbon dioxide, let's draw a Lewis structure for carbon dioxide. And first we need to get the valence electrons. For carbon, 2s2, 2p2, or you just count along line 2 until you hit carbon. That will be the 4th element. So that's 4. Each oxygen, that will be the 6th element in line 2, or 2s22p4, that's 6, and we have 2 oxygen, so multiply by 2, that's 12. Altogether we have 16 electrons, 16 valence electrons. So let's write down here valence electrons. Now let me show you how I can come up with 2 structures for carbon dioxide. The central atom is carbon and outer atoms are oxygen. So it can have central atom carbon, 2 outer atoms, then give noble gas configuration to the outer atoms, 2, 4, 6, because it already has a pair of electrons, 2, 4, 6, 8, and 8, 16. So I have assigned all the valence electrons in this molecule. However, the central atom doesn't have 8 electrons because central atom must have noble gas configuration. So what we do next is try to give noble gas configuration, and in this case, since we don't have any extra electron, if we had more than 16, you'd be placing it on the central atom. But now we don't have more than 16. So what we need to do, there are 2 ways we can give carbon 8 electrons. One way would be bringing one pair from here to here, and the other one would be from here to here. So that would give you, let me show you, carbon with 2 double bonds on 2 sides. So that's carbon dioxide, that's the one structure. Or rather than having 2 double bonds, I can have carbon, let me show you that. Carbon, let's first write down what we had. 2, 4, 6, let's make 8. 2, 4, 6, 8, it's 16. What I could do, I can bring in 2 pairs of electrons. One pair from here, one pair from here. That would give me carbon with triple bond on one side and single bond on the other side. So I'm going to now write down carbon with triple bonded oxygen and single bonded oxygen on the other side. This is 2, and here you have 2, 4, 6. So now I have 2 structures of carbon dioxide. Both have 16 valence electrons, and based on Lewis structure, both structures are right, but we are going to choose the best one based on formal charges. So let me now count formal charges on each atom, starting with structure 1. Let's label these as structure 1 and 2. So this is structure 1, and second one is structure 2. Now I'm going to first focus on oxygen 1. This is oxygen 1. Let's call it oxygen 1. The other one is oxygen 2. Now I forgot to assign those unshared electron pairs on oxygen. So let's do that before I calculate formal charge. It's very important that we do that. You would have, let me write down 2, 4, 6, 8, 2, 4, 6, 8. So you must have 2 pairs of electrons on each oxygen. Those are non-bonding or unshared electrons. Okay, now let's double check so that every atom has 8 electrons around. Okay, now let's now count formal charge for oxygen 1, for structure 1. First, you need to know the valence electrons. By looking at periodic table, we know oxygen has 6 valence electrons. So let's write down oxygen has 6 electrons. Now, because of structure formation, there will be distribution of electrons. And because of that, you'll have to find how many electrons are actually assigned to oxygen 1. Now this is how you're going to count them. So let me write down in green so that you can follow. The electrons solely on oxygen 1, that's 2, 4. So 4 of them, and take half of the shared ones, 5, 6. because those are the two bonds shared between carbon and oxygen. So what we have now assigned, let me put down here, this is valence electrons, VE, assigned electrons, I'll write down AE, 2, 4, 5, 6. 6 would be assigned electrons. Valence electrons is nothing but the number it's supposed to have. It is supposed to have 6, and in this structure it does have 6. So there is no net charge. So formal charge is 0 for oxygen 1. Now let's calculate formal charge for carbon. First get the valence electrons. 2s2 2p2, that's 4. 4 valence electron, that means it's supposed to have 4 electrons. In this structure it has 4 electrons because there are 4 bonds, 2 on each side. And remember, you just take half of that shared electrons. So half of the shared would be, out of 8 you take half, that's 4. So 4 are assigned electrons. So let's put down AE. It is supposed to have 4, it does have 4. So there is no gain, no loss. So formal charge is 0. Now let's try for oxygen 2. It's pretty much similar as oxygen 1. Oxygen is supposed to have 6 valence electrons. Let's write down 6 valence electrons. Assigned electron B, let me again show you. 2 solely on oxygen, second 2 would be, so 4 are solely on oxygen, and then there are 2 bonds, so take half of that. 2 bonds means 4 electrons, so take 2 of them. So you have 4 solely on oxygen, and 2 are coming from double bonds, so that's 6. 6 assigned electrons in the structure. It's supposed to have 6, and it does have 6. For formal charge is 0 in this structure. So what we found here is formal charge on oxygen 1 is 0, carbon is 0, oxygen 2 is also 0. Now let's examine structure number 2 on the right hand side. Again, let's assign oxygen 1 and 2 all these numbers so that we know which we are working on. For oxygen 1, what we now have is 2, 4, 6 solely on oxygen. Let me show you that. 2, 4, 6 solely on oxygen, and it's going to get 1 electron from that bonded electron pair, since it is shared between carbon and oxygen. So assigned electron to be 7. So let me write down the valence electron again is 6 for. So 6 is valence electron, and 7 is assigned electron. Remember, you understand that 6 are solely on oxygen, those are non-bonding, unshared electrons, and 1 is coming from the bonded pair because you take half of that. So 7 assigned electrons. So it's supposed to have 6, but it does have 7 in this structure. That means it got an extra electron, and that's why it is -1. The formal charge is -1 for this oxygen. Now let's work on carbon. I think I should use a different color so that we don't. Okay, the formal charge is -1 for this, and now let's try with carbon. Again, valence electron for carbon is 4, 2s2 2p2 is the 4th element in the second line. So that's valence electron. So carbon has 4 valence electrons. Let me see how many assigned electrons we have. There are 4 bonds. So carbon must have 4 assigned electrons because we take half of those electrons. Out of 8, we take half of that. So there'll be 4 assigned electrons. So it's supposed to have 4, it does have 4. So formal charge equals to 0. Let's now focus on oxygen 2 in structure 2. 2 electrons are solely on oxygen. So that's 2. And then it gets electron from 6 electrons in between carbon and oxygen. 6 electrons are coming from the triple bond. So you have 1, 2, 3 coming from the triple bond and a pair on oxygen. So there are 5 electrons. So 5 would be assigned electrons. And valence electrons for oxygen is 6. I'm assuming that you already are familiar with that now. By looking at periodic table, and you see this is in line 2, and you count from left to the right until you get to oxygen. Or just look at the outermost S and P configurations, 2s2, 2p4, that's 6. So oxygen 2 is supposed to have 6 valence electrons, but in this structure it has 5. So that means it lost one of its electrons. Loss of electron means formation of a positive charge. So formal charge for this is +1. One thing I wanted to tell you that CO2, that what we have drawn, these are neutral molecules. So formal charges added together must be equal to 0. And indeed, in structure 2, even though the first oxygen had -1, but the second oxygen has +1. So when you add them up, it's 0. So total formal charge has to be 0 because whole molecule is neutral. Now when I compare structure 1 with structure 2, I find that formal charges are 0 for structure 1, and on the other hand, structure 2, they're not 0. They're -1 and +1 for individual atoms. So best formal charge is the one that I have written on the top. The best structure is the one that has closest to 0 formal charge values. And accordingly, structure 1 is the best Lewis structure between these two. In this slide, you're looking at additional problems where NCO minus structures are shown. Let's first focus on the leftmost and focus on nitrogen. So this is the nitrogen I'm looking at. It has 2, 4, 6 electrons solely on nitrogen, and it's going to get 1 electron from the bonded pair. So 7. So assigned electron is 7. So 7 is assigned electrons. What about the valence electrons? Again, look at periodic table. Now, if you look at periodic table for nitrogen, you are going to see that nitrogen has 5 valence electrons, because the 5th element in second line, starting from the beginning of the line, keep on counting until you reach nitrogen. So let's say 1, 2, 3, 4, 5. Or just write down electron configuration 2s2, 2p3. So valence electron is 5. So 5 valence electrons. It's supposed to have 5 electrons, but assigned electron, that means it has 7 electrons. That means it gained 2 electrons in this structure. And that's why it got -2. Similarly, you can count formal charge on carbon. Carbon has 4 valence electrons, 2s2, 2p2, or the 4th element on second line, and that gives 4 valence electrons. So it's supposed to have 4, but let's see how many it has in this structure. It has 4 bonds, and it gets 1 electron per bond because they're bonded. So it's supposed to have 4, it does have 4. So there is no formal charge, and that's why it's 0. Now let's count on that oxygen. 2 electrons are solely on oxygen, that's 2, and it's getting 3 other electrons from the triple bond. So altogether we have 5 electrons, and valence electrons for oxygen is 6. 6 is the valence electrons, and assigned electron is 1, 2 solely on oxygen, 3, 4, 5. 5 is the assigned electron. So valence electrons is number of electrons that it is supposed to have. So it is supposed to have 6, but it now has 5. So it lost 1 during this redistribution of electrons. So it lost 1 electron, that's why it must have +1. In the same way, you can try the other ones, and you can come up with all these structures, 1, 2, and 3. So the question is, which one is the best? 3 is the best because that's closest to 0. And not only that, looks like 2 and 3 both would could have been a good candidate. However, when more electronegative element gets negative, that's favored. So in this case, oxygen is more electronegative and got minus. In structure 2, nitrogen is less electronegative, but it got minus. So obviously between 2 and 3, 3 is the most acceptable structure. So you'll also need to include, in addition to formal charge, first look at the formal charge, which is closest to 0. If there is more than one such formal charge, then look at the structure which has negative charge on most electronegative element. So that way we identify 3 to be the best structures.